Okay, today we're going to be talking about separable equations. So, separable equations are differential equations that are going to take this form. We have the derivative of y with respect to x is some function of x times some function of y. So, we're going to get right into this and see how we would solve something like this. Now, it's clearly separable. We have that the derivative of y with respect to x is equal to some function of x multiplied by some function of y. So now I'll just explain how we move through the steps into finding this general solution. Our goal is going to be to set it up in such a manner that we have the dy on one side and the dx on another, so that we can actually integrate one side with respect to y and the other side with respect to x. So this dx right here is in the denominator, and that's no good. So we're going to have to multiply both sides by dx. Also, we want to get all the x's together with dx. We want to get all the y's together with dy. So as when we integrate, we're only integrating with one variable. So this 3x cubed plus 1, that's going to have to get divided by both sides. So those are the two actions we have taken to move from here to here. Now we have a function of y times dy is equal to a function of x times dx. So we're just going to take the integral of both sides. Now, the integral of 1 over y plus 4 is ln of y plus 4, absolute values. The integral of 3x cubed plus 1 is 3 over 4, x to the 4 plus x plus c. Recall that when you're taking the the integral of polynomials like this, you are going to raise the power by 1 and then divide by that power. So we raise the power from 3 to 4, and then we divide the whole thing by 4. That's how we end up with 3 over 4 x to the 4. Now, you may notice that we should probably have put like a constant on both sides, but in general, we're not going to bother with that, because if I had done ln of y plus 4 plus c is equal to 3 over 4 x to the 4 plus x, plus x plus d, well, I would just move the c to the other side to get ln of y plus 4 is equal to 3 over 4 x to the 4 plus x plus d minus c. Every time we do these sort of separable equations, we're just going to skip this intermediate step, and we're just going to call this c. So that's why when we take the integral of both sides of an equation, we're only going to end up with one constant. We're going to act like we combined both those constants on the right side of the equation. Now, we have our y, which we want to isolate if at all possible, because we like to reach explicit solutions. So we want to isolate that y, but it's stuck inside this ln function. So recall that probably the best way to get rid of that is going to be to raise both sides of this equation as powers of e, because if you'll recall, just right on the side here, e to the power of ln x is just equal to x. That's a little rule we have. So e to the power of ln y plus 4 is going to get rid of that ln altogether, and we're just going to be left with y plus 4. Now, it doesn't make the right side of the equation look very cute. It becomes e to the power of 3 over 4x to the 4 plus x plus c. Well, we want to isolate that y, so we're going to move the 4 over. So moving down here, we have successfully isolated y, even though it's a rather ugly looking solution, but we can simplify it slightly. You'll notice that, I'll write another one of our rules here. If I have x to the power of n plus m, that is equal to x to the n times x to the m. So we're going to use that rule to take this e to the c term and bring it out as a factor. Now, e to the c, it's just e to some constant. There's no variable going on in there. So it's just a number. So we're just going to let d equal e to the c. This is, again, a common practice we're going to do in solving these differential equations. If you have some constant and it looks very complicated, e to the power of c plus d plus e, where they're all constants and there's no variables involved, we're just going to simplify them down to one letter. So we're going to take that e to the c and it's just going to become d. This is our final answer, although if you would like, you could further simplify. I say simplify, but you could decide if you thought this was more simple to say y is equal to d times e to the 3 over 4x to the 4 multiplied by e to the x. Because recall, just in the same way that we brought this little plus c term down, we can also bring the x term down as a power of x, if you felt so inclined. But I'm going to say that this is the simplest form, and this is our explicit solution. So to clarify what we've actually done here, we started with this differential equation, and we wanted to know what function y actually solves this. Well, when y is equal to any constant multiplied by e to the 3 over 4x to the 4 plus x minus 4, that is a satisfactory solution to this differential equation. We're going to do one more example to get us more comfortable with these separable equations, and this is going to be an initial value problem. So let's look at the differential equation dy dx is equal to secant x tan x plus x. But on top of that, we've been given an initial point. When x is equal to pi over 4, y is equal to pi squared over 32. That won't come into play until the end. So right now, we're just going to kind of do the same system we did before, where we have a dy dx, but our goal, since this is separable, is going to be to get all the x's on one side of the equation and all the y's on the other, so that we can integrate with respect to both variables. Now, there's no y's in here at all. So we're going to divide this whole thing, we're going to multiply the dx term on both sides so that we just have dy isolated on the left, and we have all the x terms along with the dx on the right. And now, just as before, we're going to integrate both sides. Now, the integral of dy is fairly simple. That's y, technically y plus c, but as mentioned before, we're going to let that plus c only sit on the right side. The integral of secant x tan x is secant x, and the integral of x is just 1/2 x squared. And then we'll, of course, finish with a plus c term. Now, this is a solution. Honestly, we have y explicitly representing the left side. We have all x's as the only variables on the right. We're satisfied that this is a solution. But this is an initial value problem. So we need to plug in the y value as pi squared over 32 and the x value as pi over 4. So secant of pi over 4 is the square root of 2. And pi over 4 squared times 1/2 gives us pi squared over 32. Now we have a common term on the left and right, so we can just subtract those. And we're left with c is equal to the negative square root of 2. We're going to plug that value into our general solution. So note that this was a general solution, but we were given points to actually solve for what c is definitively. We have c is equal to negative root 2. So our final solution is y is equal to secant x plus 1/2 x squared minus the square root of 2. But recall that sometimes these solutions aren't just true for all numbers. In this case, since secant of x is equal to 1 over cos x, we don't want cos x to ever equal 0, because then we would be dividing by 0. Well, that happens at negative pi over 2, pi over 2, 3 pi over 2, and so on. So we're going to find the interval where we can fit in the x value that we worked with, which is pi over 4. So the interval of interest here is from negative pi over 2 to pi over 2, because that is the interval where cos x will never equal 0 and pi over 4 resides in there.